Hi everyone. In this video, we will discuss Taylor series. Now, as we begin this video, it may seem a bit strange that we're going to actually spend quite a bit of the video first discussing power series, and it won't be until the very end that we are able to look back and see that we have proven many results that apply to a special type of series, a special type of power series called a Taylor series. So while we will spend the vast majority of the video discussing properties of power series, these are all properties that will be important to helping us understand why Taylor series are important. So let's jump right in and begin by looking at the following theorem. So theorem 2.72 says let f of x be the standard power series here, and let it have radius of convergence r, where we're going to assume r is strictly greater than 0. So imagine we have a power series and it has a radius of convergence that's strictly positive, right? So it's not a 0 radius of convergence. It does have some positive radius of convergence. Then we get the following three properties. So the first is that the function f, the power series, is continuous with respect to the variable x on the interval of convergence. The second piece, even though it looks like it's just giving a formula for the derivative, that's really telling us two things. It's telling us that the power series is differentiable and that its derivative can be expressed as the term-by-term derivative of the power series presentation, right? So I can actually find the derivative of this power series function by just taking the term-by-term derivative. Now, you may think in that regard, well, can't I always just take a derivative? This is a sum. I can break up a derivative over a sum, right? Well, that's true for finite sums. But for infinite sums, that's not true in general. So what we're going to prove here is that in the special case of a power series, yes, you can take the derivative term by term in the sum, even though it's an infinite sum. And also that series, so this is differentiable and the derivative is this on that same interval of convergence. So this is sort of a compact statement, but there's a lot packed in here. So this is telling us that f is differentiable. Its derivative is the term-by-term derivative, and that series now also converges on the interval minus r to r. And then number three says something similar, but instead of being about derivatives, it's about integrals. So this says that if we want to compute the antiderivative, right, of f, then we can do that term by term. Okay, so notice I still have another power series. There's my x to the n plus 1. The coefficient now is a sub n divided by n plus 1. So again, it's telling me that this has an antiderivative. It's telling me that its antiderivative can be found by taking the term-by-term antiderivative, and that power series converges on the same interval of convergence as the original series. So there's really a lot packed in here. One way we could summarize this is we could sort of say, like, if I think about this power series, and I just think about sort of coming over here and writing out the terms, right? So this would be a0 plus a1x plus a2x squared plus a3x cubed, so on and so on and so on, right? This is like a polynomial, right? But it's not because it doesn't terminate, right? It doesn't have some finite finite highest power, right? So this isn't a polynomial. But what this theorem is saying is that even though it's not a polynomial, in a lot of ways it is like a polynomial. It's going to be continuous wherever it converges. It's going to be differentiable term by term wherever it converges, and it's going to be integrable term by term wherever it converges. So again, this is a nice theorem that in a lot of ways tells us that things work exactly as they should. Now, one thing to take note of, just to be careful, right? If you look at your indices of these things, note that when we take the derivative, we lose the zeroth term. And if we write it out here, right, you see clearly if this is f, right, so if this was f of x, right, then if I was going to take the term by term derivative, right, that would be 0. I'd be left with a1 plus 2a2x plus 3a3x squared, so on and so on, right? So when I take a derivative, I lose the zeroth term because that's just a constant term. So again, just things to take note of, to be aware of as we set out to prove this. Now we're going to spend most of this video proving this theorem. So before we jump into proving this, let's first sort of make a plan. So we're going to prove 2. Okay, that's the one, the differentiation formula. The proof of 3 is nearly identical, and we'll sort of talk about that after we prove 2. And 1 follows immediately from 2. So let's back up for a second. If we look at the statement of the theorem here, right, if my function is differentiable on this interval, then it must be continuous on this interval, right? So as soon as I prove that it's differentiable, then I immediately get that it's continuous on this interval as well. So I sort of get that for free. And in fact, there are other ways using theorems we've already proven to get at that as well. But we'll just take it as a consequence of 2 once we prove 2. All right. So what's our plan for proving 2 then? Well, in order to prove 2, I'm going to, for the time being, I'm going to take my series f of x, my power series f of x, and I'm going to take this other power series g of x. And for the time being, I'm just going to assume they are sort of unrelated power series. I mean, unrelated except for the fact that they're related through these coefficients, a sub n. Okay. So the first thing that I'm going to set out to do is I'm going to show that if this power series converges, which that's one of our hypotheses in the theorem, we're assuming this converges on minus r to r. I want to show if this converges on minus r to r, then this must also converge on minus r to r. Now, that doesn't tell me anything about how else these might be related to each other. That just tells me that these 2 power series have the same interval of convergence. However, then what I want to do is once I know that this converges, I actually want to use that to show that this power series must be the derivative of this power series. Okay, so that will establish that not only do they have the same radius of convergence, but also they are the derivative of f of x is just g of x on that same interval. Okay, so we're going to break up our proof in that fashion. Now, again, if we were going to prove 3, we would do this very similarly. We would leave f of x as this. We would rewrite g of x as the term-by-term antiderivative. We would show that if f converges on minus r to r, then g converges on minus r to r. And then we would show that g of x was the integral from 0 to x of f of t dt. All right, so let's set out to do this then. All right, let's start with the first part. So what do we know? We know that f converges on minus r to r. Okay. So what would the root test tell us? So since f, another way to say it converges on minus r to r is to say it has radius of convergence r. By the root test, well, let's see. The root test says I look at the limit as n goes to infinity of the nth root of a sub n, or sorry, the absolute value, sorry, the nth root of the absolute value of a sub n x to the n, right? And the root test tells me that that f will converge if this limit is less than 1. So since I know it converges, I must get something that's less than 1 here. Okay. Okay. Well, what would that tell me? So if I look at this, I could express this a little more nicely. This is the limit as n goes to infinity of, this is the nth root of the absolute value of a sub n times, this would just be the absolute value of x. And I know that this converges when the absolute value of x is less than r. Okay, so it must be then that if I replace this with something, so let me write it this way. So if I rewrite this, I can actually pull this. This doesn't depend on n anymore. I can pull it outside of the limit, and then I can divide both sides by the limit. Now, I can do that so long as this limit is not zero. Notice that if this limit is zero, then the radius of convergence is infinite. Okay, so if this is zero, then I can deal with that as a separate case. But if it's not zero, I can do this. And I know that this this converges when this is less than r. Okay, so it must be that if I look at this being equal to r, it must be that the limit as n goes to infinity of the nth root of a sub n is 1 over r. All right. Now, why is that going to be helpful? Because now I want to find the radius of convergence for G. Okay. So now, and maybe I'll sort of carve out some space here. So applying the root test to G, I want to look at the limit as n goes to infinity of the nth root of, now I've got to look at the terms of that G power series. So the term there is n a sub n x to the n. Now, if I do a little simplification here, I'll get the following. I'll get the nth root of n times the absolute value, the nth root of the absolute value of a sub n. And then I'll again get it just an absolute, oh, sorry, actually, it's not quite as easy in this case. I'll get a limit as n, sorry, this should be to the n minus first power. Okay, this will be a limit as n goes to infinity of the nth root of the absolute value of x to the n minus 1. All right, so now if I look at each of these pieces, okay, this first piece, this is a little bit of a tricky limit, but it's just a limit of a sequence of real numbers. This limit is 1. This limit, because this is the same a sub n as over here, this limit is 1 over r. And if I look at this, let's see, what is this going to become? This is going to become the limit as n goes to infinity of absolute value of x to the n minus 1 over n. N minus 1 over n is going to go to 1 as n goes to infinity, so I'm just going to get this. And this will converge when this is less than 1, and this will be less than 1 when the absolute value of x, multiplying both sides by r, is less than r. Okay. Now, again, notice if we go back to the case, had this limit been 0, that would have meant our radius of convergence was infinite. Same thing here, that would have given me an infinite radius of convergence. Okay, so if the radius of convergence is a fixed real number r that's strictly greater than 0, then you get that G also converges when absolute value of x is less than r. If the radius of convergence over here was infinite, then the radius of convergence over here would also be infinite. Okay, so what we get here is that wherever f converges, G must also converge. Okay. All right, so that is our first step. Okay, we now know that both of these series converge on the same interval. Now the quest becomes, can we show that the derivative of f is actually just this G series. All right. So now in order to think about this, I need to go back and I need to think about, so I've got these, I know that power series F is converging, and I want to think about what that means by looking at the sequence of partial sums. Similarly, I know that power series G is converging. I want to think of it in terms of its sequence of partial sums. So I'm defining these F sub k's to be the sum from n equals 0 to k of a sub n x to the n, and I'm defining the G sub k's, again, to just be the partial sum n equals 1 up to k of n a sub n x to the n minus 1. Okay. Now, the first thing we want to observe is since these are partial sums, they're finite, right? These are finite sums. So it's in the case of finite sums, I can always take the derivative term by term. So the derivative of this is always this, right? For any fixed value of k. So for every natural number k, this holds, okay? Now, note that since the G sub k's, they converge on minus r, a theorem we proved in the previous video shows that the G sub k's converge uniformly on any closed subinterval. They converge uniformly on minus r for any r, little r, you pick between 0 and capital R. All right. Now, why is that helpful? Well, if we go back a few videos, we were talking about when you have a sequence of functions that's converging uniformly, how do you know when that uniform convergence preserves derivatives? And at that time, we wrote down a theorem which says if we have a sequence of functions, each of which is continuously differentiable. So if I look, for example, at these G sub k's, right, they are each continuously differentiable, right? I can, if I look at the f's, each of these is continuously differentiable. Each of the f sub k's is a polynomial. So it's continuously differentiable. If each one converges pointwise, we're assuming this converges pointwise. And if the sequence of derivatives, so the sequence of derivatives is just, they're the G sub k's, if those converge uniformly, then we could say that these derivatives converge uniformly to the derivative of this. Okay, and that was theorem 2.68 if you want to go back and reference that. Okay, so I can say using by theorem 2.68, since the f sub n's, or sorry, the f sub k's are continuously differentiable, Again, they're just polynomials, on minus r to r. The f sub k's converge to f on minus r to r. Again, that's our assumption. And the derivatives of the f sub k's, which are just the g sub k's, converge uniformly on minus r to r. Then this theorem 2.68 tells us that the f sub n primes, or sorry, the f sub k primes, which are again are really just the g sub k's, converge uniformly to f prime on minus r to r. But the limit, the pointwise limit of these gk's, okay, is converging to that series G, which is just the sum n equals 1 to infinity of n a sub n x to the n minus 1. And so f prime of x is equal to g of x on minus r to r. Okay. So now the question becomes, okay, great, that's true on minus r to r, but I want it to be true, it's on the closed interval minus little r to little r. But I want this to be true on the open interval from minus capital R to capital R. Well, since this holds, right, all of this holds for any little r value between 0 and capital R. And so, since this holds for all little r between 0 and capital R, then f prime of x is equal to g of x for all x in minus capital R to capital R, which is what we want. So again, in the first part, we show that this sequence G has to converge on the same interval. And then in the second part here, we show that the G that we're converging to, this power series G, it actually must be the derivative of the power series F. All right. Now, again, you could do something very similar for antiderivatives or for integration, right? So again, the proof works almost exactly the same. You have to change some of the particulars, like what actually G is, right? Because you have a different thing there. But the idea of the proof is exactly the same. And then instead of using theorem 2.68, there was a theorem about derivatives and uniform convergence. I think it was theorem 2.67 that gives you the conditions you need there. But again, you can check that those conditions are met. And again, the idea of the proof is essentially the same. So again, what this theorem is really telling us is that while power series are not polynomials, in many ways they behave like polynomials. Okay. And now another thing that follows immediately from this theorem, right? So we've seen that the theorem 2.72 showed us that we can differentiate term by term, and that gives us a new power series. Well, then you could just apply this again, right? So an immediate corollary is you actually get derivatives. It's not just one-time differentiable. It has derivatives of every order, right? So first derivatives, second derivatives, third derivatives. And you can find each of them in exactly the way you would expect. You just keep differentiating term by term. Now, that gives us sort of an explicit formula here for the kth derivative. I don't know that I wouldn't worry about trying to memorize this. This is just saying, right, okay, if I took k derivatives, what would happen? Well, First an n would come down, then an n minus 1, then an n minus 2, all the way up until this would be the last thing that came down. And then I'd be left with an n minus k power here. The 0 up to k minus 1 terms, when I'm taking the kth derivative, would all be killed off because they would all be 0. Okay, so again, this is just saying you can basically take the kth derivative by just differentiating each term in the series k times. Okay. A nice little consequence of this that we'll take advantage of here in just a few minutes is if you take the kth derivative of a power series and evaluate it at 0, then you just get k factorial times the kth coefficient. Okay, and again, that holds for every value of k. All right, so these power series are really nice. They're continuous, they're differentiable, they're integrable, they're actually infinitely differentiable. So they're just really, really nice. Again, they're like polynomials in many ways on their interval of convergence. So there's the big difference, right? Polynomials, their domain is all real numbers. Power series have some interval of convergence. Outside that interval of convergence, they diverge. So they have some limited domain unless that radius of convergence happens to be infinite. Even if the radius of convergence is infinite, they're still not polynomials, even though they're sort of polynomial-like in many ways. All right. Now, this next theorem, it actually has a sort of a nice, straightforward proof. It's not something that we often spend a lot of time saying, okay, I'm applying theorem 2.74, but it's something that's really nice to know. And that is that a series representation is unique on its interval of convergence. So to say this another way, if I have two power series and I want to know, like, do these power series represent the same function? Well, the only way they can represent the same function is if all of the coefficients are the same. Okay, so you don't have to worry that, okay, well, maybe I tweaked some terms here, but over here, they got tweaked by an offsetting amount, and so they're actually the same power series. No, a power series representation is unique on its interval of convergence. Okay, and so to see that, let's prove this quickly. So let F be a power series with radius of convergence R and representations f of x is equal to sum n equals 0 to infinity of a sub n x to the n and f of x is equal to the sum n equals 0 to infinity of some other set of coefficients. Okay. And so what I want to show is the only way this can happen is if a sub k is equal to b sub k for every value of k. Okay. Well, okay, then let's observe the following. So note that if I look at f of 0, okay, well, this tells me if I plug in 0 here, every term is going to be 0 except for the 0th term, the constant term. So I'm just going to get a sub 0. Okay. Over here, f of 0 is just going to be b sub 0. So a sub 0 and b sub 0 are both equal to f of 0. So a sub 0 has to be equal to b sub 0. Now I'm going to look at f prime of 0. Well, if I take a derivative here, my constant term is going to be a1. So I plug in 0, all the other terms go away. Same thing over here. If I take a derivative, my constant term is now b1. And then I get, all the other terms go to 0. So that gives me that a1 and b1 have to be equal to each other because they're both the derivative of f at 0. If I were to take a second derivative, my second derivative, the constant term in my second derivative would be 2a sub 2. My constant term in my second derivative here would be 2b sub 2, but note that that implies a sub 2 is equal to b sub 2. Now, in general, right, we saw that formula just a minute ago, the kth derivative at 0. Here, that would be k factorial a sub k. Here, that would be k factorial b sub k. But dividing both sides by k factorial gives me that a sub k is equal to b sub k. Okay. So, let's finish this over here. So, a sub k is equal to b sub k for all natural numbers k, and hence the representations are the same. Okay. Now, this actually turns out to be really important to the notion of Taylor series. Okay. And so that's the last thing we sort of want to get to is what is all of this stuff? We've just been talking about power series, but what does this have to do with Taylor series? Now, if you think back to our earlier brief discussion of Taylor series and maybe what your discussions of Taylor series in a Calculus 2 course, generally speaking, in Calculus 2, our notion of Taylor series is, well, we want to write down a Taylor series that approximates some function, right? So maybe I want a Taylor series for e to the x, or I want a Taylor series for sine of 2x, or something like that, right? So I have some fixed function and I want to write down a series representation for it. Well, the first nice thing is this theorem tells us there's only one with a given interval of convergence, right? So in some interval, there's only one power series representation, okay? Now the question becomes then, well, what is that? What is that one, right? And so that's what theorem 2.75 tells us. So suppose f of x is just equal to this. So this is a generic Taylor series, say, centered at A, a generic power series centered at A. And suppose it has a non-zero radius of convergence, then this function f will be, this power series will be infinitely differentiable on the interval a minus r to a plus r. And the coefficients of an are given by this, okay? So the idea is if I want to represent some fixed function f, so say e to the x, right? So I want to represent e to the x by a power series, then I better choose my coefficients in this way. And then the previous theorem tells me that's the only way to do it, right? There's no other way to do it because any other way I try to do it, right, would be a different representation. And the power series representations are unique, okay? So all of this theory really builds us up to the fact that we can write down Taylor series and there's sort of only one that's going to work, right? And then, of course, those Taylor series are power series, so you can differentiate them term by term. So just sort of as an example of how sort of all of this works together, right? The power series or the Taylor series for e to the x centered at 0, right, is the sum n equals 0 to infinity x to the n divided by n factorial. Now, and the radius of convergence here is actually infinite. Okay. So, well, what can I do? Well, if I want to take a derivative of this, right? I can differentiate it term by term. So differentiating gives me the n comes down. Okay. And if I clean that up a little bit, this would be the sum n equals 1 to infinity of x to the n minus 1. N over n factorial, a factor of n will cancel. And I'll be left with an n minus 1 factorial here. So these are all the derivatives. But the derivative of e to the x, right, is just e to the x, right? And you could say, wait, so you've gotten a different power series representation here. I thought that wasn't allowed. Well, guess what? If I just change and say k is equal to n minus 1, then this representation actually turns out to be the same as this. But I'm allowed to do all of this, right? Because I can differentiate term by term. I can take antiderivatives term by term. Um, all of this stuff just works out so nicely, in part because Taylor series are power series, and because the way you construct a Taylor series is precisely the way you need in order to make sure that the derivatives of every order match up. Okay, so if you have a function that is infinitely differentiable, and if you write down this series and find that it has a non-zero radius of convergence, then that is the Taylor series, right? We're not talking about, we don't say find a Taylor series, right? Find the Taylor series. There's only one. They're unique. So again, all of this power series theory that we've been building up really explains why we can do most of the things that we do with Taylor series in a Calculus 2 course. It's just that the Taylor series happens to be the right one in order to make the derivatives of various orders match up at x is equal to a. Now, if we had another few weeks in this course, we might also look at things like Fourier series. Fourier series essentially take these monomial terms here, right? It would take something like x minus a to the n, and it would replace them with terms that are trigonometric, like cosine of nx and sine of nx. It turns out you can use those to approximate functions. They do some things better than Taylor series and some things not quite as well. So typically we get convergence on larger intervals, but we don't get the convergence of all of the derivatives. So they tend to be good global approximations, but the derivatives could be off. So one way to think about this is you have a function f, let's say, that you're trying to approximate. And for a Taylor series, you're trying to approximate it at some point A. So if you look at the partial sums, all right, what's happening is that on some interval, say a minus r to a plus r, right, these approximations are getting really pretty good, but then outside of there, right, they're diverging eventually, right? So like these are good approximations locally, like near a, they're good approximations, and they're good approximations of the function value, but also its derivatives of every order, right? With Fourier series, what we often see is that if you look at the partial sums, they're not always good approximations of all the derivatives, but they're pretty good approximations of the function values for a wide range of values. Okay, so typically Fourier series provide better global approximations of functions, while Taylor series provide better local approximations of functions. Now, the nice thing is, if you ever wanted to go off and learn more about Fourier series, you now have all of the tools that you need to analyze them. Again, at the end of the day, they're series of functions, and we have many theorems now about series of functions. Now, some of them more specific to power series, and of course you wouldn't be able to use those. But again, series of functions, they're really sequences of functions because they're the sequences of partial sums. And we have many tools in order to analyze those. Fourier series typically aren't covered in a lot of introductory analysis classes. They tend to be covered more in differential equations type courses or other applied mathematics courses. But you now, again, have all of the resources to go and learn more about those. If you're interested, I'd recommend there's a text by Brown and Churchill, which has a lot of interesting results that are similar to the kinds of things we've seen for power series, but now which work for Fourier series. That concludes this video and our discussion of series and sequences of functions.